share screen. Great. Okay. Thanks. Yeah. So now I hope it is getting recorded. Fine. So we will, before we begin with the kind of processes we'll be dealing with, we will quickly review some facts about continuous random variables. Of course, many of you, all of you would have seen such random variables in your basic courses. All right. So all the random variables are defined on a basic probability space, which we shall denote by omega script A or mathcal A BP. So omega is the basic sample space, that is the set of all possible elementary outcomes. And script A is the appropriate sigma algebra of events. This will differ from problem to problem, situation to situation, and so on. So those things you already know. And P is the probability. So certain things we will assume that you are already knowing, are quite familiar with. So that is the definition of one-dimensional and n-dimensional continuous random variables and the corresponding probability density functions. And also the connections with distribution functions, whether it is one dimension or higher dimension. Of course, if you want to note down, you may note down. And the notion of marginal probability density functions and joint probability density function. So when we talk about joint probability density function, it concerns more than one random variable and so on. And then what is meant by independence among these random variables? So independent continuous random variables. Then expectation, variance, moments, covariance, and so on and so forth. And the standard continuous distributions, their properties and things like that. Uniform distribution on a bounded interval, exponential distribution, gamma distribution, gamma distribution has two parameters, and the normal distribution, standard normal distribution, as well as general one-dimensional normal, and also bivariate normal distributions. I presume you will also be knowing about something about the n-dimensional normal distribution. Anyway, when we come to that, I will just briefly recall certain things when they come to n-dimensional case. And certain salient aspects in the sense, these are, of course, there are certain definitions basically. Your function, by the way, if you want to jot it down, you may do so. Yeah. Yeah, function from the real line to real line such that it is non-negative for all x. And also it integrates to 1 over the whole interval. So such a function is called a one-dimensional probability density function. Probability density function will usually be abbreviated PDF. Sometimes P dot D dot F. And of course, sometimes we may sort of omit the dots to save on typing time and so on. Similarly, the n-dimensional probability density function. So in this case, the function is from the n-dimensional Euclidean space, namely Rn, and into real line such that once again, f of x is greater than or equal to 0 for all x in the domain, and the integral of fx over Rn is the n-fold integral. Remember that when we write x here in the n-dimensional space, that stands for the vector x1, x2, xn. These are all standard notations. So if you integrate this function f with respect to this dx1, dx2, dxn, that is equal to 1. Of course, so you should here also keep in mind, in many of the examples that we see, both in this case as well as in the one-dimensional case, the various density functions, remember these kind of distributions, and also many things which we would be seeing, those may have quite nice properties in the sense that they may be either continuous or piecewise continuous, sometimes may even have differentiability properties and so on. And also here we are integrating over an infinite set, infinite interval. And here similarly, this is integrated over an infinite intervals in each of these variables. So in the context of Riemann integrals, this thing is to be viewed as probably an improper Riemann integral, which is finite. And similar statement applies here. However, for mathematically everything to go smoothly, it is generally convenient to assume that this integration is in the sense of Lebesgue integral. And Lebesgue integral coincides with the Riemann integral whenever the Riemann integral exists and so on. These are all theorems in measure theory. So those of you who have taken a course in measure theory will be able to immediately sort of grasp the point or the advisability of viewing this as Lebesgue integrals. But those of you who have not had the course in measure theory need not bother. Assume that these kind of guys are well defined. Whenever there is something tricky involved, then I will make a comment on that. And in some cases, I may even use the measure theoretic arguments to prove certain things. But those of you who have not done measure theory need not be bothered about that. This is just to sort of impress on you, when you are coming from the discrete case to the continuous case, there are certain mathematical subtleties which cannot be completely ignored. That's the point. So you can keep in mind that these are the kind of the ordinary, that usual kind of Riemann integrals on an infinite interval you have seen earlier. Very often, in many situations, those things would be defined, well defined, and so on. But to be mathematically quite precise, and so that there are certain pitfalls are avoided, it is always, you can sort of assume that the Lebesgue integration theory sort of comforts you that these guys are all genuine. They have legitimacy. They are not, they are bona fide objects. They are not illegal guys. Okay. Yeah, please note it down. Okay. So this is another important aspect. Again, this also would have been implicitly or tacitly assumed even in the case of discrete random variables. However, in the case of discrete random variables, let us say binomial random variable and things like that, you can motivate the random variable, but just by describing certain experiments in terms of coin tossing, success failure experiments, and so on. And but even there, one is tacitly assuming that once the density function, let's say their probability mass function, the corresponding object is probability mass function, it is called, or sometimes it is, some authors call it a discrete density function. Once the probability mass function is defined, one assumes that we have all the necessary information concerning the random variable in our hand. We don't really go in for looking for a probability space where it is defined and things like that. Of course, if you have done a course on measure theory, that also becomes obvious in the course of that thing. So here, come to this, the situation on hand. If f is a one-dimensional probability density function, then we will assume that there is a real valued continuous random variable x on some probability space such that this function f turns out to be the probability density function of x. Consequently, one can write probability x taking value in B, probability of x taking value in a set P is integral of this function f over the set B, where B is what is generally called Borel set. I will Borel set in the of the real line. So Borel set includes nice sets like open sets, closed sets, or countable union of such sets, and so on. So for all sets which we will, all kinds of sets which we will be encountering, usually this formula would be sort of valid. Yeah. So specifying the probability density function is tantamount to specifying the continuous random. So for example, even in that discrete random variables case, binomial and things like that, you can easily motivate by some describing some experiment. But even when you come to geometric distribution, the easiest way to do it is the waiting time, the amount of time one has to wait for you to get the first success in independent trials of a success failure experiment. Like that. In continuous random variables, it is generally difficult to give that kind of example. Okay. So in these aspects which we have been talking about, it is very similar to the discrete random variables, but there are some crucial differences. We know that in the case of a discrete random variable, the probability mass function f of x is precisely probability that x equal to x. In the case of continuous random variable, it is generally not true. Unless, of course, both sides happen to be zero. Only in such cases that is true. Now, one can easily show that probability capital X equal to small x, a fixed little x, is zero for all x. Whereas it is possible that the probability density function, corresponding probability density function, f of x, is strictly bigger than zero for all x. So for that, you recall that if the function is very nice function and B is a set like AB, this denotes the area under the curve F over the interval AB. And when you take a singleton point, any curve, the areas over that is going to be zero. That is why this happens. For a continuous random variable, probability capital X equal to little x is zero for every x, every real number. And I leave it to you as a small exercise to give an example where this happens. And another way it differs from the discrete random variables is that if you have a probability mass function, that is in the case of a discrete random variable, that is always dominated by 1. Because for any x, f of x is probability that the random variable takes that particular value. So since probability is always has to be less than or equal to 1, that happens. However, in this case, the case of continuous random variables, that is not true in general. In fact, the probability density function can even be unbounded. So give an example. I'll give you some hint. You look at the appropriate gamma density. So the PDF can possibly be unbounded, but then it will still be integrable. It should be non-negative and integrable, but can be unbounded. And in the case of a discrete random variable, if you have a discrete random variable x and a function h of x will always be discrete, because the range on which h takes values will be a sort of, the cardinality will be less than that of the range of x. However, in the case of continuous random variable, h of x need not be a continuous random, even if h happens to be a nice function. It may be h of x may be a discrete random variable or neither discrete nor continuous. Of course, in some cases, h of x will also be a continuous random variable. For example, if x has a standard normal distribution and h of x is x squared, then you know what is the distribution of x squared. But in general, it may be discrete or even neither discrete nor continuous. So where h of x is discrete, take the constant function. Your x may be a continuous random variable, but all the hx happens to be x, all the x equal to 3, then that is a discrete random variable because it takes only the value c. So this is the case where the h of x is a discrete random variable. And a case where it is neither discrete nor continuous, you take this example. Take an interval AB, and within that interval, h of x is x. Outside that interval, if it happens to be x happens to be less than a, you equate it to a, and on the other side, you take it to be b. So if your random variable x can take values outside that interval AB with the positive probability, then it is easily seen that this is neither discrete nor continuous. So assume such a thing and then find the discrete distribution function of hx. You know that distribution function will always be defined for any random variable. Is also to brush up your these things about the connection between PDF and the distribution function. And another difference, if X is a one-dimensional discrete random variable, and if you take the two-dimensional random variable X comma X, that is always discrete. Because if X takes a value in a finite set or a countably infinite set, then X comma X also takes value in that. However, supposing if X is a one-dimensional continuous random variable, then if you take the random variable, two-dimensional random variable X comma X, that is neither continuous nor discrete. Again, to see this, it is not discrete, it is easily seen. To see that it need not be continuous, go back here again. In case this X is a two-dimensional random variable, okay, then this would sort of, if under B is a rectangle, let us say. So probability X taking value in the rectangle, that's going to be the integral of that PDF over the rectangle. So this behaves like an area. So with that intuition, yeah, if you want to see probability X comma X takes value in a rectangle, then you can easily see that that is going to be 0. See, basically what is this? This guy, though it is in a two-dimensional space, it is a one-dimensional guy masquerading as a two-dimensional object. It is going to take value on that line, diagonal line, 45-degree line. And you know that a line in a two-dimensional space has area 0. That's the intuition. Similarly, if you have a three-dimensional random variable X, Y, Z, then the random variable X comma Z, though that is in a three-dimensional space, it is basically taking value on a two-dimensional subspace, and that will also have probabilities. So rather, it is neither discrete nor continuous kind of case. So these are some of the differences with discrete random variables with which we are more familiar. Okay, now let us look at conditional PDF. Again, something which you have seen. By the way, all these things we want to know, jot it down, please do. So let X comma Y be a two-dimensional continuous random variable with PDF F. So that F will be called the joint PDF of X and Y. You know that. And F sub X and F sub Y be the corresponding marginal probability density functions. Then the conditional probability density function F sort of dot given X, capital X equal to little x, of Y given X equal to X, that is defined by. So this is going to be a function of Y. This dot denotes that blank, that variable. So F at little y given capital X equal to small x is the joint density divided by the marginal density of x. The joint density at xy given the marginal density of x at the point little x. And this is at every y in the real line, provided the denominator is strictly positive. It is defined to be 0 if this happens to be 0. Similarly, conditional probability density function of capital X given y equal to little y can also be defined. Note it down if you want. Again, I am just recalling certain things which you have done. Okay. So, small exercises. If the denominator, namely f sub capital X at x little x is strictly positive, show that the function, the conditional PDF as a function of y is a one-dimensional PDF. What that means is you have to show these properties. It's a very simple exercise. And this also justifies the terminology of calling it conditional PDF. So, as an offshoot of that exercise, if you have that interval AB, probability y belongs to the interval AB given x, capital X equal to little x, is precisely the integral from A to B, little small f y given capital X equal to x dy. You have to integrate with respect to y, because the value of x is known to be little x. Under that condition, so as an exercise, perhaps I should have put exercise 2 or something anyway. Verify that the conditional PDF of a bivariate normal distribution turns out to be PDF of a one-dimensional normal distribution. This is one of the very nice properties about the normal distributions. Again, I presume that this you would have done in your earlier course, but it doesn't harm you to do this again. Okay. Now we come to, please note it down. The corresponding notion of conditional expectation. So the conditional expectation of capital Y given capital X equal to small x. So that is defined by the expectation with respect to this conditional PDF. Namely, this is in the previous slide, we had seen that this function y going to fy given x equal to x is a PDF, one-dimensional probability density function. So you integrate with respect to that. So that is integral minus infinity to plus infinity y fy given x equal to x dy, provided of course the integral on the right side exists. If you a priori know that the random variable y has expectation, then it can be shown that this guy is always well defined. In the sense, if the this doesn't hold, then that would be 0 correspondingly. So you, to get a feeling for this, you try to prove this with the additional assumption that the joint density is strictly positive for all x. Then that will ensure that the conditional PDF is defined for every x. You really don't need this assumption. The intuition is that when this doesn't hold, so wherever the marginal, that is fx at x is 0, then those things won't contribute anything. In other words, only x belonging to the range of capital X only will matter. So if you assume this also, then you can easily prove this using your knowledge without measure theory. If you are already reasonably familiar with measure theory, then even this assumption is not needed. Again, this is something which you would have seen. Okay, please note it down. Okay, we'll go to the next slide. So as we have seen in the previous thing, conditional expectation is expectation with respect to the conditional probability density function. Okay, now this is a small exercise. If the marginal of x at little x is strictly positive, then you can easily see that the conditional expectation of y given x equal to little x is this. And if you assume that expectation of y exists, then this forms. Because remember that expectation of y is integral over minus infinity to infinity, integral from minus infinity to infinity, y multiplied with fxy dy dx. And if you integrate first with respect to x, that expression, you get this object like this. So if you integrate this guy with respect to x, and of course with respect to that marginal density, then what you would get is the expectation of y, provided the expectation y is well defined. Soon we will see this in a different guard. This what we have stated here is nothing but expectation of y is equal to expectation of conditional expectation of y given x. So please note it down. Next, we want to point out that this guy, conditional expectation of y given x, capital X equal to little x, is an object which you would have seen in another context also. Last semester when we did discrete random variables also, that was true, but I didn't point that out because most of you would have seen the context of continuous random. Yeah, as the title of this slide indicates, it is the regression function. So let us assume that expectation of y exists. Therefore, from the previous slide, we know that the conditional expectation of y given capital X equal to small x exists. Note that here, this object is a function of x. So to emphasize that, we write it as mx, which is basically a shorthand notation of, let us say, m sub y given x at x. So that is conditional expectation of y given capital X equal to x. So here we are going to consider this as a function of x. So x varying in R. So in this notation, this notation expresses that this object also depends on x and y. But if the context is clear, we will suppress that and denote it by just by little m. So this function x going to mx is called the regression function of y on capital X equal to little x. I'm sure all of you would have had a course in statistics and you would have seen it. And also you would have seen something called linear regression and things like that, if this function happens to be linear in x and things like that. So the conditional expectation and the regression function of the corresponding thing are same. These things have evolved in different contexts. So that in that this thing, they retain that name. Yeah, okay. Now let me just say what we are up to. See, last semester when we did conditional expectation concerning discrete random variables, we also introduced an object, conditional expectation of y given capital X as a random variable. We considered the conditional expectation of y given X as a random variable. And in that process, what we did was we defined the corresponding little m precisely by this formula. And then our conditional expectation as the random variable object is just that you take this little m at capital X. So consider that as a composition of the random variable X and the function m. This function m, little m, is a function from the real line to the real line. And the random variable X is a function from your basic sample space omega to the real line. And you took the composition of the two things so that we had denoted by m within bracket capital X. And since capital X in that case was a discrete random variable, then the little m of X, that composition, would also take only finitely many or at most countably many values. So there was no difficulty in viewing that object as a random variable, because inverse image of any of the composite function of any point in R would be perhaps the inverse image under X of finitely many points or countably many points in again in R. And for all those things, you can easily see what is the probability that it takes a value certain things, certain values. These are all countable objects. And since X is a random variable, you knew that probability that X equal to A, that always makes sense because that was how random variable was defined. Here also, we would like to do something like that. So this m at capital X, that would be the object which we'll call the conditional expectation as a random variable. But here you have to be careful. Since we have already seen in the examples that the function of a continuous random variable need not be continuous random variable, or it need not be discrete or neither discrete nor continuous, and so on. So one has to do some more work. So to do that, I am going to use measure theory. So those of you who are familiar with measure theory would be able to sort of understand it completely. Those who are not familiar with measure theory, you can feel comfortable that just as in the discrete case, m at capital X, if you put also, that makes sense, and that is a well-defined object in various contexts we would be considering. So there is no problem will arise. But however, to show you that this is another application of measure theory which you have seen, I'm just going to do that. So what we will be looking at now is that as a function of X, this is a nice function. Just like we use the word nice somewhere, no? Nice meaning open sets, closed sets, and countable union of such sets are nice. So this B here will generally be what is called a Borel set of the real or the Rn. So this is a function from the real line to real line. Borel measurable function basically means that M inverse of any Borel set is again a Borel set here. Borel set is something which can easily be generated or described in formal sense, that in terms of open sets, closed sets, semi-closed open sets, and things like that. They are basically countable, could be got out of countable union and countable intersections of such sets. The countable operations on such basic sets. So now I'm going to give the argument here. Argument doesn't end. See, this argument basically uses what is called Fubini's theorem in measure theory. Okay. So those of you who are not familiar with measure theory, you may just treat it as some kind of an abstract game which becomes essential and be amused with it when I go to. So if the marginal density is strictly positive here, we know that from our exercise that a conditional expectation of y given x equal to little x is this. And if this doesn't happen, then this is 0. Now, if the expectation of y exists, what does it mean? Y times y multiplied with little f xy, that is the joint density, that is an integrable with respect to x and y, the joint integrable over r cross r. Integral in y affects y over r squared r2 exists, is finite. Or rather, mod of that is finite. Mod of the integral of the mod of this function. Now, Fubini's theorem is a theorem in measure theory which assures that if such an integrable function, you can find the integral by iterating the integral. See, this is the integrable over r cross r will be in terms of measure theory, it will be defined in terms of the measure or the Lebesgue measure on the product space. Fubini's theorem tells you if it is an integrable function, that integral over R2 is basically integral with respect to x and then integral with respect to y over R, or the other way around. That is not the only function of Fubini's theorem. Now, suppose you take integral over x and then integral over y. Or rather, in our case, let us say integral over y first and then integral over x. If you take integral over y, then what you get is, if the expectation exists, it will be this guy. So once you do that, the resulting, I'm talking only about this integral. Once you do that, the resulting function is a function of x. And that function of x, you have to integrate with respect to the marginal density of x. For that integral to be defined, that in integration over Lebesgue integral, such integrals can only be defined for what are called Borel measurable functions. So it is integrable using that. First you integrate with respect to y, you get a function, and the resulting function x is the measurable function, is also part of the assertions of Fubini's theorem. And when you integrate this with respect to y and you get the object, it is basically this with this factor. And this is your m of x, that you get that it is a Borel measurable function. So Fubini's theorem, please keep in mind that, I mean, this is something which many people may not really realize. Apart from showing or telling you that the integral with respect to the product measure is the same as the iterated integral, it also tells you when you integrate with respect to one variable as a function of the other variable, that integrated object is a measurable function. Of course, if the function has nicer properties, here we have not, we assumed only that it is integrable, namely it is basically a measurable function which is integrable. If it is like continuous, piecewise continuous, and differentiable and so on, then using dominated convergence theorem, you can show that this M is also continuous or even better, namely it is differentiable and so on. So those of you who are not familiar with measure theory, this kind of things might give you some motivation to study that. When you have the time and the inclination and the energy. Please note it down. So now that since we are assured that this is a nice function, or rather a bona fide function in our setup, one can now proceed further. So we can now consider the function capital omega to real line defined by the composition of that x and m, just as in the case of discrete random variables. So mx, we will call this is as the mx function at an omega in capital omega is m of x omega, and it is this. So now we will show that this mx is a random variable. So what is the definition of a random variable in terms of the measure theoretic objects? Inverse image of a Borel set is again a Borel set. So since we have already proved the function little x going to mx is Borel measurable, then this follows. For any Borel set, like that is open set, closed set, and things like that, the inverse image, M inverse B, is again that Borel set. I mean, such a Borel set. And recall that if x is a real valued random variable, then for any Borel set E, the x inverse of E is a set in that sigma algebra on omega. So therefore, probability of x inverse E makes sense. This is a bona fide event. If this is not an event, then you may not be able to make any sense out of what is the probability x value in E. Please note it down if you want. So it now follows that inverse image of B under the composition map mx is x inverse of m inverse B. And we get that, you can easily verify that this is an event for any be in any Borel set. So in particular, if you take this B to be the interval minus infinity to Z, closed at Z. So the set of all omega in capital Omega such that mx omega is less than or equal to x is an event. That is how in basic courses a random variable is defined. That this should be an event for every Z in R. So this sort of ties up with what you heard of seen or a definition of a random variable without invoking measure theory. And in the discrete random variable case, these kind of things were easy to show. You didn't have to really bother about whether m or x is what kind of a function. Because after all, your function which takes value only countably many values. So the upshot of this is m capital X is as a function from omega into R is a random variable. So I think I will stop here for the day. And this object only we will call as the random variable conditional expectation, the conditional expectation as a random. If you want me to go back to any of the slides, please tell me. We can do that. So I will stop sharing now. By the way, Wednesday we will not have class. That's a CMI holiday, Republic Day. So our next class would be on Friday. And as we plan to have 3 classes per week. So all of you, please stay safe. And there is the third wave seems to be going on in many places. So please take care. And we will meet on Friday. Okay.
Thank you, sir.
Thank you very much.